Alrighty. Good morning, everyone. We're going to start off with our horrible lattice energy problem today. Oof. Big oof. We have... Oh god, and Oz has already started borking. Alright, hold on. Look at the face of guilt. He knows what he did. Okay, so the naughty... Shush, naughty one. Okay. So our goal yesterday, before we decided, forget it and threw out the problem, was we were just quickly working on... Oz, sweetheart, we have to be quiet now. We were working on the lattice energy, which was the energy required to split up an ionic compound. Sweetheart. Okay, I'm going to put you on the couch, okay? Okay, let's see if he'll shut up. Otherwise, I don't know what we'll do. We'll just have to cancel class. Wouldn't that be nice? Alright, Kevin, you want to teach while I deal with this? Aw, sweetheart. Come here. Come here. Okay. So we have, one of these we have is from our delta HF table, right? The formation of sodium chloride. Formation of sodium chloride we can get from delta HF, so that one's okay. If we look at the other two, though, we look at equation 2 and 3. Aw, sweetheart, that's not okay. Okay, you know what? I'm gonna just put him in the bathroom or something. That way, at least we'll have some peace and quiet. Okay, there we go. He can bork in there. Nobody cares. So this reaction 2, we unfortunately do not have a nice, oh my gosh, delta HF4. Can you hear him, by the way? What? How did you get out of there? I locked you in. He has come out to start borking. Aha! So Shane, let's actually see. Did I give you that one? Are you sure it's not just going to gas phase? Oh my gosh. Okay, let's try this again. I have another bathroom. I'll try that one. Come here, dude. All right, so I have I know, right? I have three doors now closed in between us, so hopefully that'll work. Okay, so Shane, let me just see if you're lying to me or not. Because I don't think there should be one for sodium ion that's gaseous. Where is sodium on this list? Here it is. Oh, what do you know? There it is. You were right. Well, fine. You're lucky. Alright. So Shane has it right. So what was it? 609? Yeah. Highly endothermic, right? Not a good thing. Okay, and how about chlorine? Don't tell me that one's on here too. That's going to make this way too easy for you guys. Let's see. Aha! That one we don't have. So that one we will have to figure out. So if we look at number 3, we actually have two processes going on. we have the diatomic chlorine. Where is this list? What list? Oh, I think he was looking at the delta HF table from thermochemistry chapter. I mean, we're in chapter 8 now, but he had gone back in time to chapter 5. Yeah, that one. Okay, so this is technically two processes that we're going to have to deal with. So we technically have the first one on the table. We have a delta HF for chlorine singly, and that one is 121.7 kilojoules. The other one, as we can see, is the electron affinity. And if we go to a different table, this one I've given to you on your homework. Let's see, where are we? Let me find that table for us. Where is it? Did I give you your homework yesterday? Someone remind me. Oh yes, I did. It's right here. Okay, so if we go to the one that has the electron affinity on it, we'll go down to chlorine. We'll see that, boom, there's chlorine at, it looks to be 348.5. Actually, it's 8.6. We'll round it nicely. So the overall would be just combining these two, right? We would say, okay, we're going to add up our 121.7, add that to our 348.6. Oh no, I had a secret equation for later. I'll hide it. Haha. Okay, no secret equations for you guys. I'm going to show you an easier way to do this, because nobody wants to do this thermochem crap. Okay, and so delta H3 would be equal to, Kevin, if you would be so kind. Technically, we would be doing the same thing for sodium. We would look it up, sodium turning into a gas, and then sodium's ionization energy would be the other one instead of electron affinity. Actually, wait, I might be able to do this one in my head. Okay, I can do it. 0.9, 6, 2, wait, I don't know how to do subtraction, guys. Thank you, Kevin. Hey, look, I got 3 of those numbers. Okay, negative 226.9 kilojoules. So overall, our lattice energy, we're going to be able to figure out by messing with all of these numbers here. So we have our delta H of formation of sodium chloride. We have the formation of the sodium ion. And then we have our ionization energy. Or electron affinity, rather. Yeah, okay, so let's go ahead and put those together. So looking at these, we're going to have to combine the delta H for the lattice energy. Let's have a look at this. Are we gonna need to mess with any of these equations? Doesn't really look like it, right? This looks like it's all okay. However, this doesn't seem right. Shane, did you lie to me about the energy for that sodium? Sodium solid gas. That seems absurdly high, though. Alright, well, we'll find out if you skip this section. I'm going to just show you an easier way to do it. But lo and behold, let's go ahead and add them up. So we're going to have... gosh, what are our delta H's? So we have the first one is 411. Second one is 609.3, and the third one is negative 226. I'm thinking that 609 should be negative. Something seems off on that to me. Let me check another resource. But you know what? Let's. Oh, no, we're okay. We're okay. We're okay. I'm lying to you guys. I'm always lying to you guys. This thing should always be endothermic. Duh. Okay. 411 kilojoules plus 609 kilojoules minus 226.9 kilojoules. Yeah, right. I know. Wouldn't that be awful? No, I was thinking this needs to be exothermic for some reason, and that's why I'm like, this doesn't make sense, but it's of course endothermic. How silly of me. Alrighty, so 411 plus 609 minus 226.9. Lo and behold, we get 793 kilojoules. Thereabouts. Okay, so that is the energy that it takes to break apart. Yeah, 17.1, but sig fig wise, it looks like we're going to just round that off. So remember that this process was the opposite of what I had in my mind. Which would be breaking this thing apart. And of course, we would imagine that to be endothermic. So the opposite of that, the two ions coming together, is going to therefore be exothermic. And that's why overall this reaction is going to be exothermic. So despite our electron affinities and ionization energies overall being endothermic, because of the lattice energy, that's why this thing is going to be exothermic. Okay, so let's never think about this again because there's an easier way to do this. Are we ready for secret formula time? I think we are. Alrighty, let's see. Let's paste it then. And the creature's mad now. Aha, secret formulas. Alrighty. So we have an easier way to do this. We can just calculate the lattice energy much more easily. Using an equation where K, or kappa, it's actually what it should be, is a constant. Creature, shut up. Or else you're going in the bathroom too, mister. And then we have the charge of our ions and then the distance that separates them. So remember, distance we were able to calculate. And remember that bond length was equal to the atomic, or rather ionic radii. Added together, right? We have done bond length before. And we also, so K is given to us, and then we just have some charges. So let's go ahead and do this for sodium chloride. Let's see if we get the same thing or if I'm just lying to you completely. So for sodium chloride, we have sodium plus and chloride minus, right? If we go to that homework that I just threw at you, that is ever so long and tedious, where did it go? Let's see. There is a table for ionic radius. So let's go ahead and look up sodium and chloride on there. So sodium's ionic radius is 116 picometers. I'm just going to put that in meters. And then chlorine, -1 is 167 picometers. Kevin, if you wouldn't mind adding those for us while we do the other thing. K is constant, who cares? Kappa, I'm sorry. Q is going to be, N would be the number on our charge, so these are both 1. So Q is going to be 1.602. Well, it's already going to be the same. Okay, Kevin, if you wouldn't mind doing that. So this tells us that the lattice energy here is equal to kappa times Q over. All right, Kevin, you're taking too long. You're fired. I can do this. 3, 8, 1, 283. Oh, 1 plus 1 is 2. This is so true. Okay, so we have our distance. Kappa was crazy constant 8.99 times 10 to the 9th joules times meters divided by Coulomb squared. We have our charge, our Q's. They're the same charge. What's C? C is coulombs. It is a unit of charge. So it's a capital C. I know it's hard to tell. But this is just a number. So all those letters over there are units. They're not other constants. Doing all this. Wait a second. Do we actually use the Coulombic charge on this? We're gonna get something super small. Oh, okay. We're good. Do it, Kevin. So Kevin will calculate this for us. Let's take a look at our units in the meantime while he's doing that. Meters cancel. Coulomb squared will cancel. So we're going to be left with joules, right? Creature shush. Alrighty, so once Kevin calculates that, we'll have our number in joules per, like, I don't know, formula unit or something. We're going to want to make that into kilojoules per mole just so that we can compare it with our last answer. Oops. Awesome. Is it really? Are you sure, Kevin? That number doesn't seem right to me. Shane's makes more sense. Oh, Kevin, did you already do the per mole thing? You didn't square it. That'll do it. Okay, perfect. Okay. Shane, congratulations. You are the new Kevin. And let's see. What are we going to have to demote Kevin to? Is he the new Tyler? Who knows? Okay. No, I'm just kidding. Okay, awesome. That makes more sense. Snail. Okay, Kevin is the new snail. K is not the Coulombic constant. K is, I don't even know what this stands for. It's some kappa. It's relating lattice energy to charge and distance. So it is a specific constant for this type of problem. The Coulomb constant is Q. Capital Q, that is. I know you guys are sick of Qs. Cool. So if we wanted to make this per mole, we would use Avogadro's number, right? So we would do this. I'm going to do it myself since none of y'all can be trusted. Yeah, it's on Wikipedia. It's from the homework, yeah. What do we get from this? Or did I say I was going to do it? Okay, I'll do it. E23. This doesn't seem right at all. 491 kilojoules? That's weird. we should have gotten the same answer as before. So somewhere in this, all the calculations have gone wrong. We should end up with the same number that we calculated from doing this. We should have ended up with this number here. So I'll do the calculations myself. Let's just worry about them later in this case, since it seems none of us are able to calculate anything today. Let's just forget this for now. And I will do the calculations myself, and I'll post that for you guys later, just because I don't want to deal with this crap anymore. Is that okay with everyone? See, Kevin, we really depend on you. We need you on your game, dude. Now you're a snail. Okay, so here's... They can have a discussion with each other now. We have iPhone 11, and then, of course, didn't square. So there we go. Yeah, you have a friend now. Okay, so I'm going to go ahead and show you the correct answer later, just because I don't want to calculate all this crap and waste time. Crawl on copper, huh? All right, you may crawl on some copper. Have fun. There we go. Okay, well, that aside, let's never speak of this problem again. I'm not going to be giving you anything on your exam on lattice energy unless it's really easy. But you will have a couple of... I see. But you will have, probably 1 or 2 homework problems on it. So, yeah, I know this totally went somewhere strange, totally unintentionally. It's because all this thermochem is just awful and everybody hates it. So, yeah. Trust me, though, we should get the same answer doing it that way. So, calculation's gonna rhyme. All right, enough of that. Back to Lewis structures. Okay, let's do a couple more. Do this one. Which method did we want to do? I forgot. Did you guys like the connect the dots method or the count the electrons method? You like the connect the dots. Okay, I like that one too. Oops. Let me just make this neater. Okay. Okay. Connecting the dots. We can do it. Here we go. Here we go. So porcelainium here will have to deal with an expanded octet, but that is okay. Remember that this is... Yes, that is what we're going to do today, Star-Lord. And let's do another one. And then we'll talk about their shapes. So if we do this, boron has 3 valence electrons. Fluorines all have 1. Connect the dots. We get all the dots everywhere. Remember, boron is special. It only wants to have 6 electrons. It's one of our unique ones. Remember, hydrogen wants 2, beryllium wants 4, boron wants 6 to make it happy. If we, you might be tempted to do a double bond to fluorine, to make it have 8, but that is now going to put formal charges on both boron and fluorine. You're going to actually make fluorine positively charged. Considering that it is the most electronegative element, that's just not going to happen. So you can never give fluorine a double bond. Not going to work. So this is actually what we're going to leave it as. So just remember, boron only wants 6 electrons. Alrighty. So now, what if I told you that the fluorines didn't like each other? The fluorines are, pretty electron dense. They do not want to be located nearby other fluorines. And we're going to see that they will arrange themselves in a manner attached to boron such that they are as far from each other as possible. All right, so if you think about fluorine atoms being just globs of electrons, those are all kind of negatively charged. They don't want to be nearby each other. So they're actually going to arrange themselves into this kind of triangular shape, not Celsius, with roughly 120 being the angle behind them. Exactly, yeah. Fluorine is like the complete diva. Like, forget it. So those will want to be about 120 degrees from each other. And that's actually going to be the best way to kind of arrange them so that they are as far from each other as possible. We're going to see that this shape is called Trigonal Planar. And this will be kind of your flagship molecule for that shape. So we have our fluorines. I'm going to omit the lone pairs for right now. Don't you dare ever do that. Never forget your lone pairs. They will arrange themselves into this triangular shape. And it is planar, indicating that this is a two-dimensional structure. So if they were to try and bonk one of the fluorines out of the plane, you would see that would mess up the bond angles. So they want to be as far from each other as possible. The best way to do that is in this kind of triangle shape around the central atom. Okay? If we look at that selenium dioxide, we just did its structure. We're going to see that it's going to kind of also want to adopt this shape. If we think about it, this boron had 3 things on it. Right? We had 3 fluorines. They don't want to be near each other. They're going to push each other away. This selenium also has 3 things on it. It has an oxygen on the right, oxygen on the left, and a lone pair. It has 3 things also. However, a lone pair is actually going to be kind of a bigger... Shush, creature. Is going to be what's the best thing to say? It's purely electrons, right? It's concentrated electrons. Where fluorine was an atom that had electrons in it, a lone pair will actually push other stuff away even more. If you want to think about it, think of a lone pair as this kind of big blob, and that blob is going to push away other things. And so we're going to see lone pairs push away other things more than atoms do. And so we're going to see that the angles here are not going to be the same. So why we might want to say, okay, yeah, they're about 120 degrees. This one here is going to be a little bit bigger than 120 degrees because it's pushing away those atoms even more. The angle I'm talking about, by the way, is kind of like this angle. If we were to just kind of go down and then I'll just draw it like that angle. That's what I'm talking about. So the angle between the lone pair, selenium, and then the oxygen. Okay, deleting that. And this angle between the oxygens and the selenium is going to be a little bit less than 120 degrees. And we're going to see that this is going to affect a whole bunch of crap that we're going to learn. So here we saw on Discord, I posted this lovely, lovely chart for us that I guess we're talking about today. I didn't think we'd get to it, but lo and behold, here we are. That's going to have all these fun shapes for us to learn. Oh, this one doesn't have the bond angles. Well, I'll give you another chart that has the angles on it. So we're going to be learning all of these shapes. We're going to have a convention as well. To describe all of these molecules in an easy way. Which is called AXE notation. So A refers to your central atom. For this class, that's always 1. So we're not going to ever put a subscript with that. For X, that is the number of outer atoms on the central atom. And E is the number of lone pairs on the central atom. So all this stuff we're going to be talking about is related to the central atom. It does not really matter what the outer atoms are. So if we look at that BF3 molecule, how would we classify this according to our convention here? We, of course, have our central atom, so that's just A. How many outer atoms do we have? Yes, Tyler, you are now promoted from snail into something else. These little arrows show what it means. So we describe BF3 as AX3. We have one central atom. Yeah, now you're a turtle. We have one central atom and 3 outer atoms. And we technically have no lone pairs. But we just typically will not even include that. So, because if it's 0, who cares? If we look at this guy, how would we describe this? It has one central atom, as always. How many outer atoms does selenium dioxide have? Yes, Tyler. Wow, you really are Kevin today. Yeah, so we would describe this molecule as being under the category of AX2E. Actually, we don't even really write the 1. We just write AX2E. Yeah. Yeah, the lack of math, that'll do it for us. We're just able to classify molecules. We're going to see everything that has the same classification is going to have the same shape and the same bond angles. So if we're able to classify our molecules under this kind of convention, it's going to help make our lives a bit easier. So let's see. Let me make up a molecule. Forget it. I don't want to do that. So, yeah. Here's your math for you. All right, here we go. Equation. Yeah, Kevin has been dethroned. So, the number of electron domains, which can be either lone pairs or outer atoms, is just equal to x plus e. So if you think about it, what is 3 plus 0? I hope we can do this math, Tyler. Let's see if we can continue our winning streak. What is 3 plus 0? Hooray! Even Kevin got this one. No. And what about 2 plus 1? Two plus 1 is 6. Very good. Yes, so, yes, indeed. So, both of these have 3 electron domains. If we were to have some crazy molecule that I can't think of that would have this, that would also have 3 electron domains, right? We're going to see anything three domains is going to be trigonal planar. At least electronically speaking. So anything that would fall under the category of having 3 electron domains, that is to say your x plus e, equals to 3, will be trigonal planar in its geometry. So keep that in mind for now. Here's another molecule. So electron domains want to be away from each other. So if we think about this, carbon dioxide has 2 electron domains, right? It's got 2 outer atoms, that's it. The outer atoms want to be far from each other. So, guess what angle that's going to be? Poof, 180 degrees. We want to get them as far from each other as possible. You stick them on opposite sides, you're done. This shape is called linear. So anything with 2 domains is linear. Let's see, do I have other examples of that? Yeah, here's one. Carbon monoxide would also be linear. If we look at carbon, it has a lone pair on it, and it has an outer atom on it. So remember, carbon will be a central atom, and it's less electronegative. So this would also be linear. Easy shapes. Alrighty. Shall we move on to the next one? Alright, I have to take Creature off the couch. He's getting antsy. Come on, little dude. Okay. How about something like this? If these hydrogens wanted to, yes, the domains are on the left side on that chart. Though they do not have the bond angles, so I'll probably put up another chart that does have bond angles for you guys. Or you can just commit them to memory. We'll make our own chart, by the way, also, but that'll be somewhere in the notes. Okay. Yes, so this would be AX4, right. Absolutely. So looking at this, you might be tempted to say, oh, these bonds are just 90 degrees apart. However, that is not the case. We're going to see that there is a better way to arrange these such that these outer atoms could be as far from each other as possible. And here's now where we start going into 3 dimensions. So previously we had planar stuff, where it was all in the same plane, no problem, because that was the best way to do it. Almost, Kevin. almost. It turns out that we would describe this in a shape called a tetrahedron. This means going in, and the wedge one means going out. I can show it to you in 3D if I take a look at some Google stuff. Let's see. Let's put on this. Let's see if that works. Of course it doesn't. We try that again. New window capture. Yes, get rid of it. Okay. We're going to try this again. Boom. Okay. If we look at it, it's going to be a tetrahedron. We're going to see that we kind of have this idea that you have ones that are kind of going back or sticking out. So this is three-dimensional. So let's see if we have some good images here that are three-dimensional. Yeah, here's a good one. So we can see that we have kind of a couple of them that are in a plane, and then we have one sticking out and one going back. And so this is kind of a pyramid, like Kevin has said, but it would be more accurate to call this a tetrahedron. So a four-angled pyramid, I guess, or four-walled pyramid. And so you can kind of see what this looks like 3D-wise. So one's kind of sticking straight up. The other three are kind of pointing down a little bit. We're going to see we're actually going to have a shape that's called a pyramid. So we actually have a couple that are called pyramids. So we're going to avoid pyramid for now. This is called tetrahedral. And the bond angle, as you might have seen, is actually 109.5 degrees. So it's better than 90 degrees, right? 90 degrees, they would be closer together. And so 109.5 would be an ideal one for us. Alrighty. So that's our next one. We're going to see that this will be for 4 domains. So something like this guy, or this guy, or this guy, let's make that CL instead. All of these would be tetrahedral. Hooray. We will learn the pyramids, square pyramidal and trigonal pyramidal. We'll learn those in a little bit. Right now I want to focus on electron geometry. Alrighty. What if we had 5 things? Turns out the best way to arrange 5 things, this would be AX5, by the way. 5 domains, the best way is actually Alright, hold on, creature is barking outside. You know, this morning they were all really quiet, so I guess they saved up all their energy for you guys. Okay. And so this one is actually called, it gets horrible, but this shape is called Trigonal Bipyramidal. So if you think about it, we're gonna have. I'm gonna show you on Google again because it's just gonna have better pictures than I could ever draw. So Trigonal Bipyramidal. Okay, here we go. We've got some lovely images on Google. So here we go. Poof. There we go. We can look at these two perhaps. We're gonna see that we have three of them or two of them sticking up and down. And then we have kind of three of them in the middle in this kind of plane. And so that's going to be this trigonal bipyramidal shape that we're going to see. Okay, so let's see. If you can kind of look here, you can see where that name comes from. So we have a trigonal pyramid on the top and one on the bottom. So two triangular pyramids are going to be there. Okay. And so anything that would have 5 domains would be trigonal bipyramidal. The distance or bond angle here is 120, but bond angle here is 90. That's just how it's going to work. So we actually have 2 different bond angles in this particular one. So anything that falls under 5 domains would be under trigonal bipyramidal. Last one, 6 domains. Six domains. Calculate them? No. Reference them on a chart? Yes. And 3D speaking, okay, maybe I can get this one. We have 2 of them going in the back. We have 2 of them coming towards the front. This is called octahedral. And in fact, let's see. Here's one. Okay. Going back to Google, this one right here is octahedral. So we have 2, one up and one down. And then we just have kind of this square thing in the middle. And so we're going to see that's how that's going to happen. Where are your ball and stick models? They're somewhere at the office. Get out of here. Google will do it for us. So something with 6 domains would be octahedral. Yes, and for that one, everything is 90 degrees. Absolutely. Yeah, so they're all right angles to each other. Okay, so that's basically, I guess, the left side of the chart that I put up on Discord for you guys. But that's what things look like electronically speaking. So these are what we call electron geometries. So that is what the shapes look like. That's how we get the bond angles and all that fun stuff. But there's always a but. Does the dark shade indicate an atom is so this dark one is coming out of the screen. So it's coming towards us, so closer. And the one that's like kind of the hashed line, that one's going further away. Okay? So wedge, dark thing coming out at you, dashed thing going away from you. But as we saw with the selenium dioxide, lone pairs ruin everything. Yikes. So we saw that the lone pair actually pushed the oxygens away. We're going to see it's going to be the same idea here. That in ammonia, for example, that lone pair will push the hydrogens away more than the hydrogens would put themselves away. And so we're going to see that the actual angle there is about 107.5 or yeah, that's about right. Thereabouts. Might be 0.9, I don't remember, but it's a little bit less. So consider the tetrahedral bond angle. That bond angle was 109.5. In ammonia, it's actually a little bit less because that lone pair pushes down further. So this introduces something called valence shell electron pair repulsion theory. Which, for whatever reason, is pronounced Vesper, even though it is spelled Viseper. We're going to see that because these electron pairs repel things more, yeah, they're strong. They're concentrated evil. So they are forceful, right? So they are going to push things away, even more so. And we're going to see that in water, for example, with two lone pairs, that bond angle is even smaller. So now we have two lone pairs pushing on those poor hydrogens, makes it smaller. So the idea here, more lone pairs, more repulsion, smaller bond angles. All right, and this is most evident in ones that are tetrahedral to begin with. These, yeah. So that's, oh yeah, right. Some random website. Yeah, exactly. So, this is actually chapter 9 now, just so we know all this stuff with the shapes. So we are in a good place. Remember, this stuff and the Lewis structures are not on your exam. That's on Monday. Did you guys want a review tomorrow, by the way? I don't think anybody has said anything. So, I'm not going to do it if nobody wants it. So, if you want me to do it, say something in Discord or here. That would be okay as well, if you want to do stuff tomorrow. And so, there are some resulting things from this. Which are called molecular shapes. So lone pairs can't be seen. Okay, Kevin wants the review. We'll do the review. Consider that a lone pair is much smaller. What homework that you're doing now? Periodic trends? Yes, that one is due. That one will be on your exam. Yeah. So that's the stuff that we do on Saturday. Don't forget it is due Saturday. So lone pairs can't really be seen per se because they're so small. They're like really close to the oxygen. They're within its normal radius. But these hydrogens would be, by comparison, much bigger. So we have another kind of way of talking about the shapes of molecules where we kind of ignore the lone pairs. So we're going to see this. So we can't see them, but we can feel them. We know they're there. And molecules see this. That's why these bond angles change. So if we go back to ammonia for a second, if we pretend, by the way, this is AX3E, if we pretend that that lone pair isn't there, erase it from existence, we can describe the shape of what is left. There you go, exactly. So long as they're not on copper, right? And so if we look about this, we have a nitrogen in the middle, and we have 3 hydrogens that are kind of pointing down a little bit. And we're going to see that this shape is going to be called Trigonal Pyramidal. So this is a single pyramid that is triangular, as it were. So let me pull up the Google. And so here we go. Let's see if we can't find some lovely... aha! This very crude drawing is exactly what I'm looking for. So if we draw it like a tetrahedron, here we go. We have them pointing down and going in the back and all that fun stuff. If we pretend the lone pair isn't there, we look at what's left over, and that is a triangular pyramid. So if we think about it, another way of describing it is looking at this one, for example. We know it's tetrahedral to begin with. And then if we kind of erase that lone pair for existence, oh, you see I was slightly off with my bond angle. Don't worry, we'll be okay. I don't know if I trust this CO part anyway. But lo and behold, we're left with a triangular pyramid. So that is how we're going to describe this shape. So we're going to see that anything that is AX3E, its molecular shape is trigonal pyramidal, and its electronic shape includes the lone pair, would be tetrahedral. Molecular shape excludes the lone pair. So we're going to see that anything that is AX3E will follow this pattern. It will be tetrahedral in terms of electron domains. Excuse me. However, it's going to become trigonal pyramidal if we look at it pretending the electrons aren't there and just looking at the molecule itself. So, oh darn, it looks like we're out of time for today. I had so much more fun to throw at you. So we will continue this on Monday then. Nope, Tuesday. Yikes, your exams are just so close. I don't want to have to write another one. Oh well. Okay, so tomorrow we want to do a review, so show up at 10:15. We'll do it then. Bring your questions. We can do some homework problems if you want. We'll continue this fun shape stuff next time. All of this is on the chart, by the way, in Discord if you want to look ahead, kind of. Instead, it's just kind of just separating it by like number of lone pairs. So it's going to be the same stuff that we're going to talk about, so just arranged a little bit differently. Alrighty, so with that, I guess I'll see you guys tomorrow, and then we'll have our exam Monday, and then I'll see you again on Tuesday. So, hooray! Okie dokie. So, and I will also figure out what the heck went wrong with the lattice energy thing, and I'll post the correct thing up later as well. Okay, so see you guys later.